Hey guys, this is just a short video introducing the idea of gravitational field strength. The first thing we did in discussing gravity in a formal way was look at the universal law of gravitation, the force law between two masses. Now we're going to talk about gravitational field. So the symbol is the symbol little g. And it really... It's the same symbol we've been using throughout, but except so far, pretty much all the time when we have been using that symbol, we've treated g as if it was this fundamental constant. In fact, it's not. It's actually a variable quantity that depends. Field is a property of mass, and it changes. It changes. The larger the mass, the stronger its gravity field. The farther away you are from a mass, the weaker is the gravitational field at that spot. So far, all of the questions we've done, we've been on the surface of the Earth where the value of g is the same, but now we're moving away from problems strictly on the surface of the Earth. And it turns out we introduce this quantity of field as a useful description of really where forces come from. So important for now, or from now on, we're not going to think of little g as a constant 9.8. It actually changes. So there's some brief notes that I've attached for you to have a look at. I'm not going to get into the derivations. It's very simple. But first, field, the units. The units that we always associated with g have been meters per second squared. But you can see from Newton's second law, F equals ma, that if I take force and I divide by mass, I get acceleration. And it turns out this equation has to be dimensionally correct. So here, units of newtons per kilogram are equivalent to units of meters per second squared. And it turns out, you will see, we actually measure gravitational field strength in units of newtons per kilogram. So these will be the units of g, this varying quantity. And really, again, if you look at F equals ma, and that is the defining equation for field. If you actually put in the force law, then we would get big G m over r squared divided by m is equal to, and instead of a, I'm going to put g for field, and I get one of the masses canceling, and I get my formula for field strength. G is big G m over r squared. So little g, a varying quantity. And I can put a vector hat here because it is a vector quantity. So it depends inversely on the radius, and it depends on the size of the mass that's producing the field. And unlike force, it only depends on one mass. Every mass has it associated with it its own field. So I'm just going to go through one quick example, and then that'll be it. So, again, as I mentioned in the last video, these questions are calculator ugly. Big numbers. So the question we'll do simply is we're going to find the gravitational field strength at the location of where the International Space Station is. So here it is. Determine the field strength. I'll put gravitational field strength of the International Space Station. And that's sometimes abbreviated to ISS. And I'll tell you that it is located 408 kilometers above the surface. So, a couple of things to note right away. One, that number 408, we won't on its own put it into a formula. That's actually called an altitude, which is a distance above the surface. In all of our formulas that we're going to use moving forward, it's always a center distance, always from the center. When we're calculating the force between two objects, it's from the center of one to the center of the other. In this problem, to calculate the field strength at a certain distance from the Earth, in that formula, for G, it is from the center of the Earth. So here, I want my R value in the formula. And I'll draw a picture here, and it certainly, well, of course, won't be to scale. There's the surface of the Earth, and from our formula sheet, we know the radius of the Earth is 6.38, 10 to the 6 meters. And then orbiting the Earth, over here, we have our International Space Station going around, and we're given this distance here, 408 kilometers. So first, again, that's an altitude. Okay, we're going to add that to the radius to the Earth's radius to find how far the International Space Station is from the center of the Earth. And be careful when you do this addition. You've got to change those kilometers to meters. So this is 408,000 meters. So in our formula, we're going to actually write R equals the radius of the Earth plus 408,000 meters, or 6.38 times 10 to the 6 meters plus our 408,000 meters. And I believe we get R equals I have it written down somewhere, 6.788 times 10 to the 6 meters. So this is the number that's going to tell us the field strength at that location. So to finish it, it's nice. I always get, well, not always. I occasionally get students complaining that I write too fast. Well, or you can actually, if I erase the board a little too quick now, you have the option of going back in the video. So let's just finish it off, okay? So here's our newly obtained formula for little g, this variable quantity. It's big G m over r squared. So again, big ugly numbers, 6.67, 10 to the negative 11. And then the mass of the Earth is on the formula sheet, 5.98, 10 to the 24. And then this radius squared, 6.788 times 10 to the 6 squared, giving us G equals 8.7. And I'll write newtons per kilogram. Now, it wouldn't be incorrect to say meters per second squared. You could also say that the acceleration due to gravity at that location is 8.7 meters per second squared. So I've put down in the notes a couple of suggested practice problems. It's really going to practice. It's going to be calculator practice and also practicing the mathematical form of the equation. The fact that g varies inversely with the square of r. If you're okay doing problems with ratios, so you can quickly say solve questions where if you double the distance away, well then since the distance varies inversely with the square, then doubling and then 1 over 2 squared is a quarter. The acceleration would, or field strength, would decrease by a factor of 4. So that's it. Okay, so I guess the most important thing to take away, little g is not a constant. It's a varying quantity called gravitational field strength. Okay, bye for now.